So we had defined a relativistic momentum, where we've seen that the difference from just classical non-relativistic mechanics. Well, in non-relativistic mechanics, of course, you had momentum as m times v. Relativistically, the only thing we're really doing was to include the Lorentz factor there. But remember, as the Lorentz factor, it was 1 over square root 1 minus beta squared, and beta is c. And we had introduced the zero, so the time component of the momentum vector as essentially being the energy. And from the invariant form vector product, we all calculated either u is minus c squared, always invariant. That's why we had to put this gamma in front of the velocity vector so that it's actually Lorentz invariant. And so p dot p, Lorentz four-vector product of the momentum with itself, is also an invariant at minus mc squared, which of course means if we're looking at photons and light with the mass is 0, because they travel with the speed of light, then p dot p is 0 for the photons. Okay, so identifying the zero component with time and the 3 momentum is the 3 space components, then this invariant four-vector product also tells us how energy and momentum are related. And in particular, for photons that means if the mass is 0, so for photons, energy and momentum are very simply related as momentum times as the energy. Okay? So, and then we did some bit involved calculations with Lorentz four-vector products that were invariant between photon energies and just velocity vectors. All remember? So we're looking at radiation being produced in some region, called it the emission region, with some energy, photon energy E, emitted at some angle with respect to our direction of motion. And then say we're stationary here, and then the emission region is moving towards us in some direction. Then we have calculated a couple of things here. First of all, we had the Doppler shift. That's what's essentially non-relativistic. You already know if the source of light moves towards you, you see everything blue shifted, shorter wavelengths, high frequencies. If the source moves away from you, you see red shifted. You get that all out of this Doppler shift formula, with this being the Doppler factor. So depending on whether you're going towards, so mu being positive or mu being negative, this becomes larger than 1 or less than 1. And then another consequence of we had 2 different expressions for this Doppler shift, depending on in what frame you measure this angle. So mu was the cosine of the angle of the photon propagation with respect to the motion direction. So that then actually told us that we see the photons going in different directions depending on what frame we're at. In particular, so we've calculated this as the relativistic aberration formula. And we stopped the movie last time actually when it was just discussing this relativistic aberration effect and this Doppler shift effect. And in particular, that means if we're looking at, say, half the radiation that comes out here in all of these directions in our co-moving frame, the angles perpendicular to the direction of motion are aberrated, are shifted towards a small angle, like 1 over the Lorentz factor of that small angle. That means half of the radiation that goes in this frame, everywhere, half the sky, is now beamed into a little small angle of 1 over the Lorentz factor. Which then also means that, well, whatever energy, whatever intensity goes into this large area here, it's now going into a much smaller area, so it must be much more concentrated. So in addition to just being blue shifted forward, also the radiation becomes way more intense in the forward direction. So you really have this small kind of headlight effect essentially all of the radiation comes out into this small angle of my polarized. So I think what we should do first is now continue that movie that now discusses still we're a little bit into this relativistic aberration effect, and then also Doppler shift and power enhancement and so on. I think we're just about at the point.
As an experiment, suppose we place a net curtain down the center of one of the cross streets.
That now gives you essentially this effect here. The curtain is essentially going
now we get back in the car
around.
Purple
You can see that that certainly appears the small angle of 1 over gamma in front of us.
Once we are moving towards it, notice it appears to be confined to a semicircle, even though it actually stretches to infinity in all directions. Its circular outline never changes as long as our speed remains constant, but the network of lines on it grow larger as we approach. We freeze as we are about to pass through it. We have reached the center of the cross street as determined by the curtain about to touch the windshield, but it is so distorted that a bulge appears to stretch towards us at eye level, while at ground level, the yellow center line of the cross street is still clearly visible. Let's play that again, this time in slow motion. The aberration of light relates where you perceive an object or event to be to where it actually is. Since length contraction distorts where an object actually is, we relativistic travelers can easily make mistakes about the state of our motion. Right now, everything seems to be moving past very quickly, much faster, in fact, than the 36 kilometers per hour speed limit. If we were to measure our speed using a street map and our dashboard clock, we would conclude that we were going almost 4 times the speed of light. Now, why doesn't the policeman who just passed, you did see him, didn't you? Why doesn't he pull us over? That is because our actual speed is still only 35.5 kilometers per hour. You would think that either our clock or our map must be in error. In fact, for us in the car, it is the reading of distances off the map that is wrong. Length contraction has caused the blocks to shorten to nearly 1/4 their normal length, and that is why we are getting uptown much faster than we might expect. To get back to the policeman, let's take a look at the scene from his point of view. To him, we appear to approach very rapidly, but slow down drastically just as we pass him. Notice how the car appears to be rotating as it passes, as though we were doing a 4-wheel slide, whereas we might appear to warrant a dangerous driving charge. In fact, our speed has not changed at all. The policeman, who is accustomed to these aberrations, relies on his Doppler radar gun, a device which still works admirably, even in this crazy world. To understand what is happening, suppose that there is a series of markers posted every 5 meters down the street, and we release a light signal whenever we pass one. The signals of our progress travel with the speed of light in all directions to whoever may be watching. To assess what was seen by the policeman, notice that as we are approaching, the spheres marking our passage are all bunched up, and consequently he sees us pass the markers in rapid succession, giving the appearance of great speed. After we pass him, the reverse is true. The spheres carrying news of our progress are delayed, making us appear to be traveling much slower than we actually are. And the rotation? This is called Penrose rotation, and to understand it, we have to consider where each part of the car was at the time it sent its contribution to the current picture. You can see in this graphic different parts of the image of the moving car are peeling off at different times and traveling towards the eye, all to arrive at the same time. This distorts the picture, making the car appear to be rotating. If the policeman were able to remove the travel time of light and reconstruct the picture as it would appear with instantaneous transmission of information, he would see our speed is constant, our car is contracted, as textbooks say it should be, and if he could see our clock, it would appear to be running very slow, recording 1 second for every 4 on his dashboard clock. This model of relativistic travel does ignore a very important property of light, its frequency, which we perceive as color. Blue light has a higher frequency, is higher pitched, if you like, than green, which in turn is higher than red. When the source of light is moving, its frequency appears to change. This is more familiar with sound waves. When we hear a car pass, we notice that as it approaches, the pitch of its engine sounds higher than when it recedes. This is the Doppler effect. Light behaves in a similar way. Approaching light sources appear bluer, while receding light sources appear redder. Suppose a source is sending out light at a particular frequency. The expanding spheres would now represent peaks of the light waves as they go out, like ripples on a pond. But once we are moving, we have the now familiar phenomenon that while approaching, we encounter the spheres more frequently. The frequency appears higher, and so the source would appear blue. And when receding, the frequency appears lower, and the source would appear red. To better illustrate this effect, we're going to turn our city a monochromatic green, a frequency that is in the middle of our range of color vision. Back in the car, we expect to see color changes in our surroundings as they move relative to us. We will accelerate very slowly because the effect is very quickly obvious. At a rather slow speed of 7 kilometers per hour, the full spectrum of our vision surrounds us, ranging from blue in the front to red in the back. Accelerating a bit more, at 9 kilometers per hour, or meter equal to 0.25, we lose the ability to see the outside world behind us. Because the light has been shifted out of the visible range into the infrared. At 12 kilometers per hour, a beta of 0.33, we can no longer see where we are going because the light in front of us has become ultraviolet. Looking sideways, where objects are neither coming towards us or going away, you might expect to see the original shade of green we chose for the city. But that is not quite right. What you see is closer to yellow. Now this is rather like a replay of our earlier experiment with clocks. The source of light behaves like a clock, sending out its time signal at very high frequency. The general caveat that moving clocks should appear to run slow applies to light sources also. All moving sources slow down. That is, they head towards the red, or, in this case, green gets about as far as yellow. This is sometimes called the second-order Doppler shift. On top of this, the ordinary, or third-order Doppler shift, does its usual job, shifting light that is coming from ahead back toward the blue. And light from behind is be shifted further into the red. Recall that we ran out of the red end of the spectrum first. Meantime, we are heading down the road, unable to see where we are going. This is getting very dangerous, so let's stop. That was a close call. Our model has yet to account for one more thing, the intensity of the images. Approaching light sources not only turn bluer, they also grow brighter, while receiving light sources not only turn red, they become dim. The intensity or power of incoming light is distorted as we travel. To isolate this effect from the Doppler shift, let's turn off the exterior color, because our eyes register intensity differently for different colors. As we start to move again, the scene grows brighter, especially right in front of us. When we reach 16 kilometers per hour, look around carefully. It gets darker as we look back behind us. Now look out the front windshield again. We will accelerate 22 kilometers per hour, a beta of 0.64. The scene before us is starting to get completely washed out. At this speed, the television picture or projector cannot reproduce the intensity we should see in front of us, whereas looking around again, the scene behind is dark to the point of not being able to see anything much at all. Since the screen cannot show the difference between bright and blindingly bright, we get a false impression of what lies before us. To get around this problem, the obvious thing to do is wait for nightfall. Or something that happens very rapidly at these altitudes, as you can see. Very soon, the light level has decreased to 5% of its daytime value, so we can still see a little. Set up again, accelerating very rapidly to a beta of 0.5, 0.6, 0.7, 0.8, 0.9. Clearly now night has become day to the extent that even Las Vegas might be jealous. We now see a bright spotlight, and as we clear this tunnel, accelerate again, we see that the spotlight condenses in front of us. We are now traveling at a beta of 0.995, faster than we've ever traveled before. The center of the view is nearly 10,000 times brighter than our television can show, and if we got any closer to the speed of light, it would just grow brighter, while the spotlight would diminish in size, eventually to a point. Is this what we would really see? No, because we've turned off the Doppler effect, and the bright radiation in front of us long ago shifted out the visible range. If we turn the color back on and return our vision to its normal range, all we can see is a faint rainbow at the edges of the windshield. But remember, it is nighttime. Wait, dawn approaches, and we will soon reach a new day. The rainbow is not visible now, but we are still left with very little to look at. Until we slow down again. As our speed drops, the rainbow broadens. Slowing down even more to barely a floor, we find the spectrum surrounding us again, much as it did without the power distortion. Except that in the back, it's still too dim to see anything. And in the front, the blue and violet end of the spectrum is much brighter. To end our holiday in this virtual world, it would be a shame not to enjoy the thrill of traveling at speeds even closer to the speed of light. We won't worry about the Doppler effect or power distortion, as this prevents us from seeing anything much. So here we go. Beta is 0.99, 0.999, 0.9999, 0.99999. Help me, one to stop. Thank you. We hope you have no problem adjusting to the world where the speed of light has its conventional value, and that you enjoy this short exposure to the reality of relativity.
So, that was it. I think we can all agree that it's easier to move non-relativistically. Get some kind of orientation, right? Okay. Alright, so we should go on doing a little bit more relativistic kinematics, essentially working a little more here with momentum vectors. And much of relativistic kinematics you can actually infer just from momentum conservation, right? You know that from classical mechanics, non-relativistic physics, both energy and momentum are conserved. That means we have any kind of reaction, whatever energy and momentum goes into the reaction is the same that goes out afterwards. The nice thing is now that essentially energy and momentum conservation are pretty much the same thing, because it's just the conservation of the total for momentum vector. So, notes here. So the basic principle to start out with is the momentum before, let's call that P goes in. So that would be some of all particles that go into some kind of reaction. So let's call that I that goes in is the same as would have to come out, right? So so let's call that the total momentum that goes out of the reaction. So the textbook gives us one very simple example, that you have one mass m here slamming straight into another mass here, and what comes out, the postulate is that it comes out with some kind of total mass m, assuming that it's perfectly inelastic. That means nothing bounces back, they just stick together here. And because the speed was 3/5, so they go with speeds. So beta of 3/5 and here beta equals 3/5, only in the opposite direction. The question is how much mass will come out there. Okay, so to do that, we can say what is the momentum, the total momentum going in. So of course the sum of the four momenta of these two particles, right? So let's say this one goes, say, in positive x direction, and this one goes in negative x direction. See that? Then, well, what's the four momentum of the particle? Gamma mc times 1 and beta is this particle because it goes forward beta direction, and then we have another one, gamma c1 minus. Alright, and what comes out in the end? We have something that's just at rest. So there's no gamma, gamma is 1. We have just mc and the 4 vector, if something's at rest. Then if it's at rest, there's no velocity here. So of course the space components are 0. So it's then just 1 and 0. So this of course means the momentum is 0 here, it's 0 there. We've already been sure of that. Because we have the same masses, the same Lorentz factors. We can figure out what the Lorentz factor is. And the Lorentz factor is 1 over square root of 1 minus beta squared. So beta squared is 9 over 25. So that is 5 over square root 25 minus 9 is 16. And so that is 1 over 4. That's our Lorentz factor. So, because here we have already said that the 3 momentum in equals 0, and that's the same that comes out, right? Because the final mass is at rest. But then we also have, for the time component, for the 0 component, we have 2 gamma mc equals mc, right? Now, 2 gamma is 5½ mc, so that means the mass that comes out is 5 over 2. Does that make sense? So if there were no relativistic effects, you just have 2 balls that stick together, the mass would be just twice. It would just be the sum of the masses. But now we see this equivalence of energy, kinetic energy and mass. Actually, the kinetic energy that these balls have, if nothing is dissipated, that actually adds more mass to the final state. So it gives us the equivalent energy in mc squared. So whatever kinetic energy is here is converted to just produce more mass in the final state. Just a quick question, is that a realistic scenario? Can you imagine any scenario in which you actually have 2 balls sticking together and the complete energy all just transformed into mass? What would rather happen? What do you think? It's probably not perfectly inelastic, that's right. And also energy will probably be dissipated in other ways. Let's say that this thing heats up and radiates stuff away or so. So in any realistic situation, we will not really end up with that. It's just the mathematical example. Okay, so we have another example. Then we can start that. So it's here. We're done with all this. Second example that we have is that we start out with an unstable particle that is a mu1 with typical mass of the mu1. And what happens with that is that it's unstable, it decays, so that goes in, and what comes out is, well, it will be, actually it's a pion decay, right? Yeah, sorry. can do the same muon decay as well, but it gets a little more complicated. So this is an unstable pion, say pi plus. So with a mass m pion, and what comes out is that you have in one direction muon going out, and in the other direction you have neutrino. Neutrino essentially behaves exactly like a photon. It's just a different kind of particle, but also massless. Almost massless, we now know they actually have a little bit of mass, but for the argument here, we can assume that a neutrino mass is 0. Which is a good approximation. Then we can play the same game here. So what is the total momentum that comes in? That's only the pion at rest. Right? So pion at rest is pion mass c, 1, and there's no velocity here. Right? So down equals 1, and we take 0. And that should better be the same as what comes out. That is, well, the velocity of the momentum vector of the mu1 here. Let's say that's E mu1 over C and P of the mu1 plus we have energy neutrino over C and, well, this, okay, let's call this P neutrino. And we know that energy of the neutrino must be P neutrino times C, right? Because they're massless. So our M equals 0. Okay. So then, first thing we can see from the energy equation is that m pi c, let's just multiply c over everywhere, and pi c squared equals E plus mu. And so the rest mass energy of the pion is converted to the energies of the mu1 and the neutrino. And then, since there's 0 momentum, we know that these must go exactly in opposite directions. So we can say that P of the mu1 equals minus P of the neutrino, and they're going in exactly opposite direction. So what we can do now is, so for the energy of the mu1, energy of the neutrino, but so these are the absolute values, must therefore be the same. So we have Pu equals, so that's the absolute value, is P mu, that is energy of the neutrino over C. Right? So what we have here, so that also means that's the energy of the neutrino is P mu. But P mu we can solve for this. Right? If we solve this, we can solve for the momentum as square root of, so times c, that is E squared minus C squared. Right? So we can use this here as 1 over C u on energy squared minus C squared. And we can plug this in here. So it's E mu plus square root